this last class, right? So যেটা তোমরা মনে রাখতে হবে is just these two things. আজকে হচ্ছে we'll look into combination of springs and energy interaction of springs. Okay, so last class we saw that there are materials that don't have a limit of proportionality, but they have an elastic limit, right? And then we saw there are materials that have no elastic limit, but they are proportional, which means that neither of these actually obey something called the Hooke's law. So for your object to be capable of obeying Hooke's law, it has to be both linear, straight line, and also it needs to be elastic. And you can see that very easily on a spring. So spring graph, you'll find that there's a point on the graph of the spring, and that point there, it is both the point till which the material is elastic, it is the point till which the material is linear, right? So therefore this is the elastic limit. So the point I'm trying to make here is that elastic limit, the limit of proportionality, right? They don't need to be at the same place, they can be at different places. Okay, and there are materials that have elastic limit and Hooke's limit, elastic limit and limit of proportionality at different places as well. A blue color line, so you'll find that till this point it is linear, but it's elastic for a much longer length, right? But that doesn't mean it's obeying Hooke's law entirely. So it's only obeying Hooke's law for the initial part there, okay? Because till the initial part, it is both elastic and it is both linear, okay? So yeah, that's what we saw last class. Hooke's law states that force and extension are directly proportional till the elastic limit, and that's about it. So এখন যেটা করবো আমরা তোমরা হচ্ছে পেজ 15 এর নিচের এই জায়গাটার মধ্যে হেডিং দাও। Yes. What is the difference? Can anyone answer his question? What's the difference between elastic limit, limit of proportionality, and Hooke's limit? Last class online. What is the difference? Elastic limit, limit of proportionality, and Hooke's limit. Right, so it's the point at which the material shows elastic behavior, right? Okay, that's elastic limit. And then right, so force and extension are directly proportional. That's the key word there. Okay, and Hooke's limit? Hooke's limit is the place where the limit of proportionality, the elastic exists. Right, correct. That's true. But when you write the definition of Hooke's limit, you say that it's a point at which the material shows direct relationship with force and extension and is also elastic. Okay, so hopefully better. Yeah, so that's the difference here. Right, so next is something called the spring constant. Eta hocche graph থেকে দেখবো আমরা। Rubber band and yes, but rubber band হচ্ছে কোনো plastic deformation হয় না, spring it is plastic deformation. So rubber band যখন হচ্ছে you go beyond the elastic limit ছিঁড়ে যায়, spring when you go beyond the elastic limit ছিঁড়ে না, but এটা permanently deform হয়ে যায়. Shape, right? Exactly. Right. So screen 2. So you have your graph force versus extension, and let's say there are two springs that we want to compare. So এখন যেটা আমরা শিখবো is trying to compare two different springs out there. So these are two different springs out there. What you need to figure out is which spring is easier to deform. So এই দুইটার মধ্যে কোনটা deform করতে হচ্ছে easier. And it's pretty straightforward, the process. So what you need to do is you এটা analysis এর জন্য বলছি, okay? পরে আমি তোমাকে আগে দেখাই দিব। So তোমরা যেটা করবা একটা force select করবা, random একটা force like this force here, okay? So you select this random force value there and see which material extends and how much for the amount of force. So if you look at the blue line here, the blue line extends to that one, right? Or that force. But the red line is not really extending much, so it's still that much, right? So if you were to compare using words, right, it's qualitative analysis. When you talk about this in words, if you want to compare the material, can you tell me which material is stiffer, more difficult to stretch? The red or the blue one? Definitely the red, red one is more extension, much for the force you apply, whereas the blue one extends substantially longer, right? So the idea is that the red graph is of a spring that is stiffer, right? On how do you do this? There's an easy way out here. What we do here is we define the gradient of the graph. And once you find the gradient of the graph, review of your quantity, that will help us figure this out better. Okay. So gradient of the graph that you get from this graph is change in y by change in x, which is force by extension. And gives you a constant value here. But constant value, if you have noticed, is only valid for the linear part. So according to graph chart, it deform with it, where your material can permanently deform. Talking deform the color. I know you can find gradient, but the gradient doesn't mean anything. Okay, so you look for the part that's earlier. Earlier part, you get a value of k, right? And this k is what we refer as the spring constant. It's a number that we use to compare spring. And you'll find that the higher the value of spring constant, the stiffer your spring is. I'll give you a very simple example for this, okay? Spring A, the red one here, okay? Irrevolutably. So spring A is spring constant 20 Newton per meter. Our blue spring data, spring B, the second spring, has a spring constant of 5 Newton per meter. What does these mean? By the way, the unit for spring constant is Newton per meter. It tells you that the first spring, right, the red spring, will stretch how much for one, how much force is needed for 1 meter. The first one. It actually 1 meter stretch korte chai spring ta, how much force do I need to apply? 20, right? And the second one, 1 meter stretch korte, how much do I need to apply? Just 5, right? So doesn't that mean the red one is stiffer, right? And I can think there comes a very simple way of analyzing this thing. The steeper the graph, the stiffer the material. Do you understand what I mean? Graph jato steepness barbe, material jato stiffness barbe. And that is one of the reasons why we prefer a what versus what graph, force versus extension. আমরা যদি extension versus force করতাম তাহলে উল্টা হইতো, যত stiffness বাড়তো তত steepness কমতো. And then that doesn't really sound intuitive, but you know, why just do that if you can just change the units, right, on the axis, and steepness will mean stiffness, right? So one of the reasons, are a better reason, this is one of the reasons. Okay, so what does that mean? That your steepness of the graph represents stiffness of the material. Okay, so steepness represents stiffness. And what is stiffness? The ease or difficulty in deforming your material. So that's what stiffness is. So yeah, I can take like a formula. So formula to gradient is equal to f by x, which is equal to k. Therefore, f equals to kx. Achha. I believe in some books and some places you might see this formula a little different. Kyoki notice so if you have seen this formula, have you seen it been different anywhere? And if you have seen it different, what have you seen different about this formula? F equals to kx. Oh no, f is proportional to x, and to remove the symbol, we put in k. But with this f equals to kx, there's an alternate variation. Have anyone seen this? Alter. No. K. Half kx square. No, that's energy formula. Acha, তুই না দেখে থাকো একটু better. Acha, so যেটা হবে আমি আগে থেকে just বলে রাখি, you'll find in a lot of books they write f equals to minus kx, minus sign there. And the reason behind that is, তুমি যখন force apply করো, doesn't your material stretch this way, right? But the force that the material experiences, right, or is exerting is actually which way? The other way. So if you think of spring, right? আমি যখন spring কে আমি force দিচ্ছি, right? I'm bringing the spring down. The spring is experiencing a force which way? Upwards. That's the tension, right? So ওই tensioner formula is the F here. So extension টা হচ্ছে উল্টা দিকে হয়. So basically the idea is that wherever you have a spring, তুমি যেদিকে এটাকে strain করবা, স্ট্রেসটা কোন দিকে অ্যাক্ট করবে? উল্টা দিকে, right? আমি এটাকে এদিকে strain করি to the left না তোমাদের right. So তোমাদের right এর দিকে যদি strain করি এটাকে, না তোমাদের left না এটা? Yes. তোমাদের left এর দিকে যদি এটাকে strain করি, which is the stress acted? The other way, right? আবার আমি এটাকে যদি compress করি, if I take it the other way, right? Doesn't it push me back outwards? So that the force and extension always act in what direction to each other? Opposite direction. And opposite in math is represented by minus. The minus indicates that, okay? So আমি তাও লিখে রাখবো because অনেক সময় বলতে পারে, জিজ্ঞেস করতে পারে, okay? So alternate একটা formula. Does it change absolutely anything about our understanding of springs? No. Okay, so math করার সময় কোনো জায়গায় sign টা use করা হবে না. It's symbolic. It's just saying that force and extension are always against each other. It does eventually become a significant factor, by the way, A2 দিকে, okay? Yeah, যারা বুঝো না, আমি just দেখে রাখি briefly কি. So you have a spring here, unstretched, and then you take the spring and you stretch it. So as you stretch it, there's an extension this way, and the spring is pulling you that way. So the force and extension are against each other. Again, if you make the spring compressed, the compression is that way, and the spring is trying to go out the other way. So you'll always find that this force and the extension work against each other. Essentially, the tension that you have in the spring is a restoring force, বলা হয়. It's trying to bring back the system to its original state. The tension in the string. Now, তুমি দিচ্ছ এটাকে deform করার জন্য, right? So you take it to a new location. ছাড়ার পরে, it always goes against whichever way the extension is. So for the thing is, the F here is trying to show you the force acting on the spring, the force exerted by the spring. Okay, so this is the force that the spring is exerted. So তুমি যেদিকে stretch করবা, the spring will always apply force which way? Opposite direction. ওটা বের করার? Oh, it was just F equals to kx because তুমি যে force দিচ্ছ, extension will always be in the same direction. Is compression shown in graphs? Yes, compression show করা হয় এই graph না, আরেকটা graph আছে we'll learn, but just to show you compression কেমনে normally show করা হয়. A extension force are a minus extension data and negative force is compression. So compression graphs গুলো এদিকে হয়, extension graphs গুলো এদিকে হয়. Extension the material can permanently deform. Compression material permanently deform হয় না, ওর একটা পয়েন্টে গিয়ে আটকে পড়ে. So that part is compression there, and that part is your tension. Not for springs, for materials. Yeah, so what happens if you press it using a press, hydraulic press? হ্যাঁ, so hydraulic press এ করলে যেটা হয়, ওটা কিন্তু deform হয় না, ওটা হচ্ছে arrange হয়. It's basically beaten down into sheets. Have you heard of malleability? Hammer করতে 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 you can just make it into a thin sheet. That's what's happening. It's a little different than what single compression is. Compression is what your springs undergo. Once you break it down into thin sheets, ওটা কিন্তু আর spring থাকে না. It'll squeeze up into some random ball of metal. Okay, so that springs don't exist when you try to compress beyond a point. নষ্ট হয়ে যায়. Right, so আমি একটা নোট দিই and then energy টা start করি. So spring constants, do you have any questions? Spring constant is a number that we use to compare springs, right? And the higher the value, the stiffer your spring.